Hi everyone, welcome to the Earth Science Regents Review podcast series created by Hommocks Middle School Earth Science Department. Today we're going to be talking about the topic of the shape of the Earth. In order to understand the Earth, we need to bring models into the classroom. Models are going to help us understand how the Earth is going to work. Obviously we cannot take a field trip out into space and view the Earth from space, so we need to bring those images into the classroom through the use of models. Now the Earth has different portions that interact continuously with each other. We have the rock portion called the lithosphere, the gas portion called the atmosphere, the water portion called the hydrosphere, the ice portion called the cryosphere, and the living portion called the biosphere. All those spheres are constantly interacting with each other simultaneously. Now way back when we had early navigation and the maps were not very good and navigation was kind of limited to a very small area, a lot of people believed that the Earth was flat. Well, we have a couple evidences here that suggest otherwise, that our Earth is actually round. The first evidence, space photos. It's the number one evidence. Space shuttle goes out in space, snaps a picture of the Earth, you're going to see an image that looks like that. That looks pretty round to me. That's the best evidence that the Earth actually has a spherical shape. Second evidence, sinking ship theory. This is kind of an ancient idea that the Earth was flat, because when sailors would take off, they'd appear to sink at the horizon. They weren't really sinking at the horizon. They weren't falling off the edge of the Earth. They were following the curvature of the planet. This is the second idea that the Earth was round. The third idea, which is very important, is the altitude of Polaris. And really the thing that you need to know here is that the altitude of Polaris equals the latitude of the observer. Altitude just means how high in the sky a star is going to be. In this case, Polaris. Navigators realized using an astrolabe, which is an instrument that determines elevation in the sky, that the angle that Polaris produced was exactly the same as their latitude that they were sailing at. So if you're at 90 degrees north at the North Pole, Polaris can be directly above you at 90 degrees. If you're at 42 degrees north here in New York, the altitude of Polaris can be 42 degrees above the horizon. If you're at the equator, which is 0, the altitude of Polaris can be 0 as well. The way you find Polaris is by finding the Big Dipper and using the two stars in the front part of the Big Dipper to find Polaris. Polaris is actually the last star in the handle of the Little Dipper. And as our stars revolve around Polaris as they move through the sky because of our rotation here, stars actually don't move. It's our rotation that's causing them to move. You'll see that Polaris, which is kind of right in the middle there, okay, is not going to move, or it's going to move very slightly. So it's kind of easy to figure out where Polaris is, not only by finding your constellations, but find the one star that's pretty stationary in the nighttime sky. You see this navigator, he's determining an angle from the horizon to Polaris. That angle is going to equal his latitude. Stars' path across the sky. Because stars, including our own sun, takes a curved path across the sky, that's going to suggest that we have a curved surface to the Earth, which can suggest our planet has a spherical shape. So you can see the stars taking their path across the sky. We're looking south in this animation here. You see the moon moving in a curved path. You can see our own sun moving in a curved path. So really important to understand the curvature of the path, and that's all caused by our Earth's rotation. And then finally, lunar eclipses. Anything that has a curved surface is going to create a curved shadow. Well, if you take a look at a lunar eclipse taking place, you can see that curved shadow on the surface of the moon produced by the curved surface of the Earth. Now there's two shapes to the Earth that we need to identify with. The first one is what we call an oblate spheroid. Basically, because of Earth's rotation, the Earth flattens at the poles and bulges at the equator. This is the true shape of the Earth. You compare that with the apparent shape, basically what the Earth appears to look like. It appears to look like a perfect circle. Now there's two pictures that just passed by you. The oblate spheroid was highly exaggerated. I want to tell you that was not set to scale, because the difference in polar diameter compared to equatorial diameter is so little, the Earth is going to look like a perfect sphere. So models of the Earth are going to make them look perfectly round and perfectly smooth. So a good example of a good model is going to be something that's going to be a scale model or something that's drawn to scale. A good example of that would be a ping pong ball or a billiard ball. They're perfectly round and perfectly smooth. One way to support the idea that we have an oblate spheroid, that we do not have a perfectly spherical planet, it's slightly flattened at the poles and bulging at the equator, are gravity measurements. Because you're a little bit closer to the center of the Earth, you're going to weigh a little bit more at the North Pole. Because you're a little bit farther away from the center of the Earth, you're going to weigh a little bit less at the equator. So because of these gravity measurements, which are ever so slight, okay, that's going to suggest that we do have slightly oblate planet. So the true shape of the Earth is what we call an oblate spheroid. So you can see here that Mr. Red at the North Pole, he's technically closer to the center of the Earth. He's going to weigh a little bit more. Mr. Blue is at the equator. He is technically a little bit farther away from the center of the Earth, which can support that he's going to weigh a little bit less. So with this diagram here, what you're looking at here is that from North Pole to South Pole, because the Earth is squished at the North Pole and South Pole, that diameter is a little bit smaller than the equatorial diameter because the Earth kind of bulges at the equator. So that's what we call the oblate spheroid. Definitely know the difference between the true shape and the apparent shape. Know the difference between the two. With that being said, thank you for your time, and we'll talk to you soon.